Good afternoon. So we'll talk about an important concept related to matrix multiplications today, namely the inverse of a matrix. And we're going to make some connections with real numbers because remember what I said, although many of these tools are just simple algorithms, whenever possible when we have time, I'd like to give you a little bit of insight on the motivation for these tools. Although some of these applications that you'll encounter later with this concept, you will encounter them later. But we can still make some motivation in terms of connections with real numbers. So we learn a multiplication of a different entity than a real number, right? The multiplication of a matrix. And the concept of an inverse is, again, something you may ask yourself for any multiplication. If you go back to real numbers, in order to talk about an inverse, we need to talk about the identity for that multiplication. So we know already that for real numbers, the number 1 plays the role of identity. So that means if I multiply any real number by 1, kind of messy here, on both sides, you get the same number for any real number, a not equal to 0. It'll be true with 0 as well, but I'm going to focus on non-zero numbers because only for non-zero numbers we can talk about an inverse, as you'll see later. So you need to know what the identity is, which in the case of real numbers is just the real number 1. And then you can say that if you have a real number not equal to 0, b is an inverse of a, or the inverse of a because it's unique in this case, if a times b is equal to b times a is equal to 1. So when you actually write a times b equal 1 and you solve for b, that is why you can denote b as a inverse, a to the negative 1, which is read sometimes as the inverse of a. So that's basically the connection with real numbers. What can the equivalent of an inverse be in the case of matrix multiplication? Can we talk about this concept? Does any matrix have an inverse? And so on and so forth. And so let me state right from the beginning that the concept of an inverse of a matrix, so the concept of the inverse of a matrix holds for square matrices only. That is because you want to have the multiplication on both directions. So for example, given a matrix A, do we have a matrix B such that A times B is equal to B times A is equal to the identity, let's call it IN. So let's imagine that we talk about n by n matrices, right? So matrices with n rows and n columns. So you need to have the same number of rows and columns simply because otherwise there's no way A times B will be equal to B times A, because the product will have different rows and columns if the number of rows and columns is not the same to begin with. So IN, the identity matrix, which remember from last time is the matrix with ones on the main diagonal and zeros elsewhere. And this is basically the matrix that plays the role of 1. So I'm going to illustrate the algorithm in order to find this inverse of a matrix if it exists. So if it exists such B, it is denoted by by A inverse. So B can be denoted by A inverse, just like for real numbers. So to illustrate the algorithm, let's actually use what we learned from systems, and then we can show how to find the inverse of a matrix using basically a recipe or an algorithm. So let's illustrate how this works for a 2 by 2 case. So let's say the matrix A is given by the entries 1, 2, 2, and 3. And so the question is to find a matrix B, and let's actually denote the entries by columns using x1, x2 for the first column and y1, y2 for the second column. So the question is to find such a B, if it exists, such that A times B is equal to I2. So in this case, 1, 2, 2, 3 times the matrix that I'm supposed to find, such that this is equal to 1, 0, 0, 1. So that is the question. Now I want you to pay attention here and notice that, I mean, you may not notice right away, but if you look carefully and do some matrix multiplication here, this equality actually hides two systems in two unknowns. So remember how we obtain the first and this how we obtain the first column on the matrix product, right? So each of the entries in the product come from row and column multiplication. So this one right here in this corner comes from row 1 times column 1, and the second entry in the first column comes from row 2 dot product column 1. And we're going to write out what that means immediately, but that's how you come up with the product, right? In fact, maybe it's just easier to maybe actually let's just do the product altogether, right? So row 1 column 1 is going to be x1 plus 2x2, and then normally you go by rows when you do the product, right? So the second term on the first row will be 1 times y1 plus 2 times y2, and then the second row 2x1 plus 3x2, and finally 2y1 plus 3y2. This should be equal to 1, 0, 0, 1. So if you set the columns equal to each other from left and right, you obtain two systems, right? So the second column will be comes from like I said, row 1 column 2, which should be 0 in this case, and then row 2 column 2, which should be 1. So you have two systems to solve. The one in x1 and x2 comes from setting the first columns equal to each other. And we're going to solve these side by sides because I want you to notice something as we move along. So let's actually draw a vertical line here. And send the second system, y1 plus 2y2 equals 0. And then 2y1 plus 3y2 equals 1. Okay, so this is an easy 2 by 2 system. Normally we don't, we don't need to do Gaussian elimination just for 2 by 2 equations. But in this time, for this example, I'm going to use Gaussian elimination because for larger matrices, it's kind of required for the algorithm to be efficient. So I'm going to use this Gaussian elimination. I'm going to produce in the end the most efficient, the simplest possible matrix of the system, which is the reduced row echelon form. So we're going to go through the row echelon form and then continue and find the reduced row echelon form. So the matrix, the augmented matrix of the system is 1, 2, 1, 2, 3, 0. We have already the first leading one. So we need to produce 0 below it. So for that we do minus 2 row 1 plus row 2. And the next matrix will be 0. Let's see, minus 2 times 2, that's minus 4 plus 3 minus 1. And then 1 times minus 2 plus 0. On the next step, let's try to be a little bit more efficient. We already know how to make the second leading one. So we're going to do row 2 times negative 1. But let's do already the 0 above it, because the next step will be to produce zeros above the leading ones. So this operation completes the row echelon form. And then when I make the 0 above it, that's going to be reduced row echelon form. So we're going to also do row 2 times 2 plus row 1, which will make zeros above the second leading one. So from bottom up, the last row will be 0, 1, 2 after I multiply with minus 1. And then the old row 2 times 2 plus row 1 will give me 0 above the second leading one. And so that's going to be minus 2 times 2 plus 1, right? So the last entry minus 2 times 2 plus 1 makes it minus 3. So the thing I want you to pay attention here is to notice that whenever you have a unique solution for a system with the same number of rows and columns, that is only basically true for square matrices, right? So for the systems, when I say a square matrix, I mean the matrix corresponding to the coefficients, not the right-hand side. So whenever you have the same number of equations and unknowns, and the system has a unique solution, you always end up with the identity matrix on the left side once you complete the reduced row echelon form. Okay, so again, that's always true if you have the same number of rows and columns and the system happens to have a unique solution. This is essentially the easiest possible stopping point of a Gaussian elimination, because to actually solve the system now, you just read the solution, right? So the first equation is x1 times 1 plus 0 times x2. So that just gives you x1 equals minus 3. And the second equation is 0 times x1 plus 1 times x2 equals 2. So the second equation just gives you x2 equals 2. So you could say that in the reduced row echelon form, if you have the identity matrix to the left of the vertical bar, the last column is the solution of the system, basically. That only happens for square matrices and if the system has a unique solution. And let's solve this one as well. And I'm going to just write down the remark that I just said right now with what happens with the format of the reduced echelon form. So here we have 1, 2, 2, 3, and 0, 1. Just like before, the first step will be to multiply the first row by negative 2 and add it to the second row. So the matrix will be 1, 2, 0, 0, minus 2 times 2 plus 3 minus 1. 0 times minus 2 plus 1, that remains 1. And just like before, we could quickly multiply row 2 by minus 1. And we could also make the 0 above it by multiplying the second row, the row 2 by 2 and add it to row 1. From bottom up again, we have 0, 1, minus 1. And let's see, 1, 0 above, and then 1 times 2 plus 0 makes it 2. Notice again that we obtain identity matrix on the left, which tells you that the solutions happens to be the right column. y1 equals 2, y2 equals minus 1. So the inverse of the matrix I just started with, so the inverse of the matrix 1, 2, 2, 3 is the matrix, remember these were by columns, x1, x2, that makes it minus 3, we obtain minus 3 and 2, and then the second column y1, y2, that was 2 and minus 1. We're going to actually check this product right now, just to convince ourselves that this is indeed the inverse of this matrix. And you should check the same product in reverse, like the inverse times the original matrix, just to convince yourself that this is indeed the identity. So 1 times minus 3 plus 2 times 2, then 1 times 2 plus 2 times minus 1, 2 times minus 3 plus 3 times 2, and then 2 times 2 plus 3 times minus 1. Okay, so check the computation for yourselves. This is going to be minus 3 plus 4, that's 1, and 0 in this corner, minus 6 plus 6 is 0, 4 minus 3 is 1. And so we managed to squeeze everything in here. So the good news is that we're going to go a little bit faster actually on the algorithm, because we can notice something right away. Namely that some of these steps were repetitive basically. So we could do a better job in finding the inverse in much fewer steps. In other words, you will see later, these two systems can be solved at the same time, basically using the same process. So, and you can save a lot of time. And I'm going to show you that on the second page. But for now, I want you to notice that the entries on the left side, so to the vertical bar, didn't really change, right? So I mean, we solved two systems, but the left side of the two systems is the same. What changed was just the right-hand side, because you solved for the two columns, x1, x2, y1, y2. So in other words, we could actually do these two systems at the same time. Nothing stops us to augment the original matrix with both columns, because it involves the same row operations. So in both cases, since the solution was unique, you ended up with the identity matrix to the left of the vertical bar. So you can solve both systems at the same time by simply augmenting the matrix of the system with both columns 1, 0, 0, 1. That is the core issue, I mean, the crux of the algorithm. So I did this detour because on the second page I'm going to show you the algorithm, right, that you're supposed to use when you do the inverse. But I did this detour because I think it's important to understand that in the algorithm of finding the inverse, you basically use Gaussian elimination to solve multiple systems at the same time. You solve a linear system for each column in the unknown matrix, basically. So you, for each identity column, excuse me, for each column of the identity matrix. So if you have an n by n matrix, you actually solve n linear systems at the same time. So stay tuned for the second page where I'm going to basically put these two together in the same format, in the same augmented matrix, and then we can move on with some other example. All right, so how do we find the inverse of a square matrix A with n rows and columns? Because again, remember, the concept of an inverse is just for square matrices. So here are the main steps. So step one, and then we're going to illustrate with the previous example and then some new examples. Augment the matrix A with the identity matrix. Okay, so you're going to basically take the matrix that to begin with and you augment it with IN. Step two, find the reduced row echelon form of A augmented with IN. If the inverse exists, the reduced row echelon form looks like identity matrix to the left of the vertical bar. So you always end up with the identity on the left and some other matrix B to the right of the vertical bar. Anything besides that, it means the inverse doesn't exist. And again, I'll show you an example right away. So once you're done, then the last step, of course, is to write the inverse to be B, right? So I mean, the inverse will be basically red to the right of the vertical bar. When you're done with the reduced row echelon form, what's on the right of the vertical bar is the identity matrix. So in our example, and we could do this a little bit faster because we already did all of the computation previously. Instead of solving separately the system for x1, x2, right, in which the right-hand side was 1, 0, and separately the system in which the right-hand side was 0, 1, we just augment with both of them, and we proceed with the reduced row echelon form steps just like before, and we could do this much faster. So again, minus 2 R1 plus R2, that gives me 0, minus 1, 1 times minus 2 plus 0, 0 times minus 2 plus 1. Then we could, let's do one more step. We could multiply by minus 1 the last row, 0, 1, 2, minus 1. And then finally, we make 0 above the second leading one by multiplying the second row, minus 2 times row 2. So the second row times 2, minus 2 plus row 1. 0, 1, 0, 1, 2, minus 1. And on the top, 1, 0, 2 times minus 2 minus 4 plus 1 is minus 3. And then minus 1 times minus 2 plus 0 makes it 2. And then notice that minus 3, 2, 2 minus 1 is what we obtained earlier. So now we finish the algorithm, right? So that's the reduced row echelon form. And we stop when we have the identity on the left. And whatever is on the right-hand side is going to be the inverse matrix. So A inverse is minus 3, 2, 2, and minus 1. Okay, we're going to do another example, this time a 3 by 3 matrix. And this is where you actually really see the power of the Gaussian elimination, because you will save so much time involving these, involving this algorithm. Okay, so suppose I start with a matrix given by the entries 1, 3, 0, 0, 1, 0. I'm sorry, I copied by mistake an intermediate step. So the original matrix, let's write it here. So the original matrix is 1, 3, 3, 1, 4, 3, 1, 3, 4. So to find the inverse, we're going to augment the matrix with the identity matrix, which in this case is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So I want you to pause for a moment to realize how powerful this technique is. What you're doing here, you're solving 3 linear systems in 3 unknowns. So if you take classical means for each of them, you're going to spend a lot of time. But because the left side of the system is the same, with Gauss elimination, this is going to be a breeze, given the fact that you solve essentially for 9 variables in total, right? So for all 3 columns. Now, of course, this is a little bit easier than average because you already have leading ones. So we make this example a little bit easier so we don't have that many more steps. We have already 1. We're going to make zeros below it by subtracting row 1 from row 2 and row 3. So minus row 1 plus row 2, change row 2, minus row 1 plus row 3, change row 3. There's going to be 0, 4 minus 3 is 1. I gave myself a little gift with the second leading one. 3 minus 3 is 0. 0 minus 1 is negative 1. 1 minus 0, 0 minus 0. Row 3 minus row 1, 0, 0. 4 minus 3 is 1. And then 0 minus 1, that's negative 1, 0, 1 minus 0. Now, obviously, in some cases you have more steps. Here I just made it so that I have already leading ones. So, but sometimes you are lucky, like in this case, and you notice that after one step, you are already at row echelon form. You have the leading ones and the zeros below them. All you got to do is to proceed further and make zeros above the leading ones. Remember, when you go from reduced echelon form to reduced row echelon form, you start from bottom up. So now I'm going to use the last row, make 0 above it. One of them exists already. You need to make 0 instead of 3. So that's going to be minus 3 row 3 plus row 1, and now change row 1. It's very important to go in reverse order when you go from REF to RREF, because otherwise you will undo the previous steps. So for now, I'm going to copy the last row, copy the second row, because we didn't touch that one right now, because already it has the 0 in the correct position. But now we change the last row. So 0 times minus 3 plus 1, that stays 1, which is our intention. 0 times minus 3 plus 3, that guy remains 3. 1 times minus 3 plus 3 is 0. And minus 1 times minus 3 plus 1 makes it 4. This is 0, the second guy, and then 1 times minus 3 plus 0, that's minus 3. So now we move to the second row, again from bottom up. The only 0 to make is above the second leading one. So we need to make a 0 above this guy, this 1, and we don't touch the last row anymore. And to do that, we just multiply by minus 3 row 2, and we add it to row 1 and change row 1. Everything else stays the same. Once again, going from REF to RREF is the same process that you started with, but bottom up instead of top to bottom. All right, so we have, like I said, 0 times minus 3 plus 1, that's still 1. This becomes 0. This is 0. Here we have to be careful not to mess up the computation. Minus 1 times minus 3 plus 4 makes it 7. 1 times minus 3 plus 0, that's minus 3. And then 0 times, minus 3 is still 0, so that remains minus 3. So we have that the inverse of the matrix is 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. I'll leave you as an exercise to check that A times A inverse is indeed the identity. Okay, so multiply using matrix multiplication this matrix and convince yourselves that this is indeed, it'll give you the identity matrix. So let's finish with an important remark. Not all square matrices have an inverse. There is a different way to check for this, namely the determinant, but we're not going to talk about that for now. I'm going to show you how you actually figure out if the matrix doesn't have an inverse as you go through the process of Gauss elimination. And I can anticipate already you will know it doesn't have an inverse when you have an inconsistent system. Remember, you solve 3 systems at the same time. So the vertical bar is the equal sign of the system. If you have zeros on the left, like an entire row equal to 0, and non-zeros entries on the right, that means you have an inconsistent system. And you stop as soon as you get that situation. So suppose, for example, I want to find the inverse of the matrix 1, 2, minus 1, 0, 1, 3, 1, 3, 2. We augment this with the identity matrix just like before. And just like before, we proceed with Gaussian elimination. So the first row is good as it is because it has a leading 1. There's 0 below it. So second row for now is good. All I got to do for now is minus row 1 plus row 3 in order to make 0 below the leading 1. So it's 1 minus 1, 0. 3 minus 3 is 1. 2 minus negative 1 is 3. 0 minus 1, 0 minus 0, 1 minus 0. If you're really careful and you paid attention to what we discussed so far, you should already notice that you have an inconsistent situation over here. Remember, that's like a system, right? So I mean, if you write the entries left and right, if you come up with the system corresponding to the first column, this will be like basically y plus 3z equals 0, y plus 3z equals minus 1. So two equations with the same left-hand side, but different entries on the right-hand side, which can never be a solution. If you don't spot this from the beginning, you just go over several more steps in the Gaussian elimination. So the next step is to make zeros below the second leading one. And we do that by subtracting row 2 from row 3. So row 3 minus row 2 if you want. And that'll give me 0, 0, 0. Minus 1 minus 0 is minus 1. 0 minus 1, 1 minus 0. So again, when you have 0 zeros and then non-zero entries after the vertical bar, that means the inverse does not exist. Because when you solve for the inverse, you end up with an inconsistent system. Basically, if you read the equation corresponding to this column, the last equation, this will read basically 0 times x plus 0 times y plus 0 times z equals minus 1. Or whatever the notation for the variables, doesn't matter, but clearly 0 can be equal to minus 1, so therefore the inverse doesn't exist. Remember the sign of inconsistency in terms of how you see it in the Gaussian elimination. Zeros below the bar, non-zeros entry to the right of the bar. But with a little bit of practice, like I said, you can spot these in situations earlier if you look carefully and you notice that the system may not have a solution. For those who will study determinants, there are other ways to recognize that, but that's not our objective for now. So with that, that's it for the inverse of a matrix. We're going to finish this chapter with the next lesson in which we'll talk about some interesting application of economics. I would say, namely the Leontief model, one of the two, the closed one, we're going to talk about it. I would say that's essentially our first real-life application that really makes use of nice mathematical tools, which without them won't be so easy to solve those kind of real-life problems. So I hope you will enjoy that when the time comes to talk about the Leontief model. And that's it for today.